All right, let's get into it. Today we're cracking open a cosmic case file on an object called Messier 53. Now, at first glance, it's this absolutely gorgeous glittering ball of stars. But as you're about to see, it is hiding some seriously strange secrets that are making us rethink a lot of what we know about these ancient star systems.
So where do we begin our investigation? Well, we have to journey deep into the northern sky, to a constellation called Coma Berenices. That's Latin for Berenice's hair. Now, to the naked eye, it looks kinda empty, but trust me, with the right telescope, we find our main suspect hiding out.
And there it is, M53. You gotta think of this less as just a cluster and more like a massive celestial city, absolutely packed with over 500,000 ancient stars, all held together in this tight gravitational dance.
So it looks pretty standard, right? Just another beautiful globular cluster. But here's the thing, it's not. Recent studies have uncovered a bunch of weird anomalies, clues, really, that make M53 a genuine astronomical puzzle. So what on earth makes it so strange?
First things first, let's get our bearings. This star city is not exactly down the street. It's about 58,000 light-years away from us, way out in the Milky Way's halo. Its incredible distance and isolation are actually part of what makes it such a perfect, untouched laboratory for studying the early universe.
Okay, before we get any deeper, let's just do a quick refresh on what we're dealing with. M53 is a globular cluster. You can think of these as ancient relics from when our galaxy was first forming. They're these tightly packed balls of stars, all born around the same time, often more than 10 billion years ago. They're basically fossils from the dawn of time.
All right, time to pull out the magnifying glass and look at our first piece of evidence. And it all comes down to the residents of this star city. The stars themselves. See, when we look at the population of a typical globular cluster, we expect to see a certain kind of family photo. So inside any of these clusters, you've basically got two main families of stars. You've got the first generation. These guys were born from the really clean, simple gas that filled the early universe, just hydrogen and helium mostly. Then you have the second generation, which formed a bit later from gas that was, polluted by the heavy elements cooked up inside those first stars.
Now, here's what's normal. In almost every globular cluster we look at, it's the second-generation stars that run the show. On average, something like 68% of the stars belong to this newer, more chemically complex family. This is the standard, it's what we expect to see.
And this is where M53 just throws the rulebook out the window. It completely flips the script. Analysis shows that a whopping 73% of its stars are those pristine first-generation types. It's a city populated almost entirely by the galaxy's original inhabitants. And that brings up a huge question. Why? Why is it so different? That is mystery number one.
Okay, so that's clue number one, a very weird family portrait. Now for clue number two. To dig deeper into these places, astronomers rely on a very specific type of star. These things are like cosmic lighthouses, and they are absolutely essential for measuring the universe.
We're talking about a special kind of star called RR Lyrae variables. They're old stars that have hit a point in their life where they start to pulsate. They get brighter, then dimmer, over and over again with an incredibly regular rhythm. You can think of them like perfect cosmic metronomes, just ticking away with a steady beat for billions of years.
And here's why that metronome is so incredibly useful. The speed of its pulse, its period, is directly tied to how bright it truly is. So if we measure how fast it's blinking, we know its real brightness. Then we just compare that to how bright it looks from Earth, and boom, we can calculate its distance with amazing accuracy. It's one of the most reliable tools we have. Or at least that's how it's supposed to work.
So we've got these super reliable, predictable cosmic clocks inside M53, right? Well, this is where our case gets really, really interesting. Because it turns out the heartbeat of this cluster isn't steady at all.
This is the question that really gets us to the heart of the M53 mystery. What happens when our most dependable measuring stick starts to get wobbly? It's this thing called the Blazhko effect. And honestly, it's a puzzle that's been driving astronomers nuts for over 100 years. It's when an RR Lyrae star's nice, regular pulse gets this weird secondary wobble. Its brightness and its timing start to change over weeks or months. It's like our perfect cosmic metronome suddenly develops a stutter.
And in Messier 53, this stutter, it's not a rare thing. It's everywhere, an absolutely staggering 66%. That's 2/3 of a specific type of these pulsating stars show this bizarre Blazhko effect. Now, in most clusters, this is a curiosity. Here, it seems to be the rule.
Let's be really clear about what that number means. This makes Messier 53 the undisputed champion, the record holder. It has the highest percentage of these misbehaving stars of any globular cluster we have ever found, period. It's this unique natural laboratory for studying this century-old puzzle.
Okay, let's step back and look at the evidence board. We have a star city that's almost entirely made of first-generation stars, and its most important citizens, the standard candle stars, have a really unsteady heartbeat. So what does it all mean?
This table just lays it all out, nice and simple. A typical cluster, dominated by second-gen stars. M53, it's all about the first-gen. A typical cluster, these stuttering Blazhko stars are rare. M53, it has more than anywhere else we know. And it all seems to connect back to that idea of chemical simplicity, what astronomers call extremely low metallicity.
So the case file on Messier 53 looks like this. We're looking at a surviving relic from the very beginning of our galaxy, a place built almost entirely out of the universe's first stars. And for some reason, we still don't fully understand, this ancient, chemically simple environment seems to be the perfect breeding ground for that mysterious Blazhko stutter. The fact that these two weird things are happening in the same place strongly suggests they're linked, and that gives us an incredible opportunity to probe both the physics of stars and the conditions of the early universe.
And that's really the heart of it, isn't it? Messier 53 was just another pretty object in the sky until we looked closer and found this deep, fascinating mystery. It's just a powerful reminder that there are still huge puzzles about our own galaxy waiting to be solved, sometimes hiding in places we thought we already knew. It just makes you wonder, what else is out there?